Yeah. So by taking all these concepts, we're moving on to the how does the compiler support towards or with para virtualization, right? So although this para virtualization reduces the overhead, which do occur in terms of problems. So firstly, its compatibility on portability may be in doubt because it must support the unmodified OS as well. Secondly, the cost of maintaining para virtualized OS is very much high because they may require deep OS kernel modifications. Okay, so kernel is a program which always run when you boot up the system, isn't it? And finally, the performance advantage of this para virtualization varies greatly due to most of the works varies from one type to the another type. Comparing with comparatively, if you want to make a differentiation among the para virtualization and the fully virtualization, this para is relatively easy and very much more practical compared to full virtualization. But there is one problem with full virtualization. What is that is it's low performance in binary translation. Okay, so you know very well, which is common, that to machine level language it has to be converted into binary representation, right? So this is what the problem with full virtualization, and to speed up the binary translation is also becoming very difficult, right? And these kind of virtualization products employ only one virtualization, that is para virtualization architecture. Okay, now these architectures which have been used very which are very much popular are Zen, KVM, and VMxWare ESX. These are the very good examples of hypervisors. Clear. Now coming to the KVM, which is denoted as kernel-based virtual machine. It is a Linux para-virtualization system, which is a part of a version of kernel, that is 2.6.20, right? And in this, what happens is all kind of functionalities like memory management, scheduling, the activities in terms of tasks are carried out by the existence of kernel. Clear. Now, one thing you can notice over here is what is that operating system is being talking about is a Linux operating system. Okay, in Linux operating system, the shell is to be used where our program is being translated and carry forward to the system is bash shell. Okay, this bash is I mean, this is a full form of born again shell. It means this was the shell which has been created by born person. Okay, not born, it is born, bourna. Clear. Now the KVM does the rest, which makes it simpler than the hypervisor, which controls the entire machine. Okay, so it was not only always busy with all these functionalities, but also sometimes it been rest. And there's one more thing which has been mentioned in the last point, that it is also a hardware assisted para virtualization tool. So what is the use of this tool is it improves performance and supports unmodified guest OS. Okay, so I've been talking about the guest OS and the host OS, right? So it improves in terms of performance and also it supports. So which kind of operating system does it support is Windows, Linux, and Solaris. So those days they were used to use Unix operating system, right? Now, unlike full virtualization architecture, which intercepts and emulates privileged and sensitive instructions at runtime, this virtualization also handles some instructions at during compile time, right? And this guest OS, which is in kernel, is modified to replace the privileged and sensitive instructions with what hypercalls, okay, which is made to a hypervisor. The name of the hypervisor can be Zen or VMM. Many terms are there which can be called as a hypervisor. Okay, it differentiates what operating system you switch to. Right. Now, as I said, the name what I suggested here is Zen, isn't it? Zen assumes para virtualization architecture. Okay. So what happens is the guest OS running in the guest domain. Okay, it may run ring 1 instead of ring 0. I'll show you the figure. See, it runs a ring 1 instead of ring 0. Okay, this is how it is assisted in terms of rings during the hypercalls. Okay, and then that implies that the guest OS may not be able to execute some privileged instructions, and these privileged instructions are implemented by the hypercalls to the supervisor. The same thing is being mentioned over here, right? And after what all the replacement has been done, the instructions with hypercalls and the modified guest, everything will emulate the behavior of the original guest OS. Okay, so this is what the general para virtualization which support in terms of compiler, right? Now here we have another example. I'll directly show you this figure. The name of this example or this figure depicts as VMware ESX server architecture using para virtualization. We have been seeing what are the drawbacks of full virtualization. So that is why author has switched it to para virtualization to be discussed in detail, right? So VMware company has developed some tools, virtualization tools for desktop systems and servers as well as virtual infrastructure for large data centers. Okay, so ESX is a VMM. ESX is a VMM or a hypervisor for this x86 symmetric multiprocessing servers. Okay, and it also accesses all the hardware resources you can see over here, IO, memory, or say scheduling, etc., etc. And this ESX enabled server consisting of four components. Okay, so they are virtualization layer, a resource manager, hardware interface components, and service console. All of this. Okay, and to improve the performance, this server employs a para virtualization architecture in which VM kernel interacts directly with the hardware without involving the host OS. I repeat, VM. In this architecture, this VM kernel directly interacts with the hardware. Okay, so without involving the host OS. Okay, so this VMM layer, what does it do? It will virtualizes the physical hardware resources. Okay, physical hardware resources such as CPU, memory, network, and disk controllers, and some devices. Okay, so every VM has its own set of virtual hardware resources. Here we are not talking about physical hardware resources. Everything is virtual. Okay, when you see such things, when you run some softwares at the bottom or the properties of that application or which is lying behind the screen, you can see all these things are allocated to individual CPUs. Apart from that, all the bandwidth of the network, okay, all these things will be maintained in a data structure, right? And the hardware interface the VMware ESX servers file system as well, right? And this entire service console is responsible for booting the system, initiating the execution of the VMM and resource manager. And not only that, it also facilitates the process of system administrators. Okay, it means which thing has to be invoked itself, and which VM is requesting which hardware device. Okay, so everything will be taken care. Next, coming to the virtualization of CPU, memory, and IO devices. This is what we have seen at the downer layer, right? Now see, to supporting to the virtualization, processors such as 8x86 employ a special running mode and instructions, which is known as hardware assisted virtualization. Okay, so in this way, the VMM and guest OS run in different modes. Okay, and all other sensitive instructions of the guest OS and its applications are trapped in the VMM. Clear? And to save the processor states, it means which process is switching to, I mean, which resource, and which process is exchanging information to which process. So everything mode switching is done completely by the hardware. For example, here we are talking about the x86 architecture, right? So this architecture usually provided for Intel and AMD processes, which have property technologies for hardware assisted virtualization, isn't it? So I mean, the providers or the designers even also have to look over which processor supports and which VMM will be able to accomplish the task. Everything compatibility checks has to be done priorly itself. Okay, now coming to the how does a hardware support when it is in virtualization mode? Okay, so modern operating system and processes permit multiple processes to run simultaneously. Okay, so if there is no protection mechanism in the processor, protection is very much important, isn't it? If there is no case, absence of protection, what happens? All instructions from different processors will access the hardware directly, isn't it? There are less number of hardware, okay, but more number of processes. So whichever process is ready for an execution, they just come and directly access the hardware. So like this, we doesn't know how many processes have been created before, how many are trying to attempt to access the hardware directly. So what happens? If there's any problem with the program point of view, then it also crashes the entire system. Clear? Therefore, all processors have at least two modes. Okay, so basically the processor can be seen in two ways or two modes, user mode and the other one is kernel mode. Clear? Here it is mentioned, see, user mode and supervisor mode. This supervisor mode can also be called as kernel mode, okay, or privileged mode or system mode. Clear? These three are the other terminology of supervisor mode. I repeat, every processors, how many processors do we have? See, multiprocessing means what? Having multiple processors and each process is allocated with one process. Clear? So here, as per this statement, all processors should have at least two modes, user mode and a kernel mode or supervisor mode. Clear. Now, what is the advantage of having these modes is instructions running in supervisor mode are called privileged mode. I repeat, the instructions whichever are running in supervised mode. It means, see, do I bother whether which device is to be allocated to user? I mean, which device is to be allocated to me? If I have two devices connecting to my system as the resources, I don't know. I just completely put a request to the computer that I want to use this. Do I instruct that I want this, I want this? It is upon it depends upon our choice, isn't it? To which thing we put a request. But what does the system do? It will invoke the system call. इसको बुलाता है कि now your resource you is under the control of this processor. Clear. Now, what does it do? Everything will be taken care by the system itself. Then, whichever instructions, whichever system calls are executing under the system mode is known as privileged instructions. In other words, if instructions running in supervised mode or kernel mode or system mode or privileged mode are called privileged instructions. Clear. Now, defaultly, if other instructions are executed in unprivileged mode, it means what? I I I I have a Java software installed in my computer, right? Now I open the shell prompt to type my program. Now, as soon as I'm done with typing a program, what do? I compile the program, right? Now, what I'm instructing the system? I'm instructing the system that now you have to compile this program, right? Now, do I bother which system files, library files, all those things, necessary files should be invoked? No, I just instruct the system that I want the desired output to be prompted on my screen. Clear. Now with that it indicates what all the system will do it. The system will completely switch to kernel mode and this will take care of ये program execute करने के लिए कौन सी चीजें चाहिए. Does it require the console IO routines or not? Whether to print the output on the disk or not. Okay, all these things will be done in when the system is in kernel mode. Okay, now let me ask you one more point. How does the system know whether the call is come from user mode or a system mode? Yes, the operating system will come to know with a mode bit. Okay, mode bit. So mode bit is the capacity of holding only one value, either 1 or 0. Okay, if mode bit is equal to 0, what does it mean is the complete entire system is in kernel mode. Clear. If the mode bit is equal to 1, it means the complete system is in user mode. It means user is doing something. Clear. Now, in a virtualized environment, it is more difficult to make OSs and applications run correctly because there are more layers in the machine task, and at the same time, many hardware virtualization products should also be available, isn't it? And then uh, when this VM workstation is a virtual machine software suite for x86 and x86-64 computers. Okay, so this software suites allow users to set up multiple virtual computers, this type of computers. Okay, after setting up all these multiple virtual computers, they can use any one of them simultaneously. Okay, by hosting the operating system. So what happens? VM workstation thinks that it assumes it is purely a host-based virtualization, right? And there are a famous hypervisor that is Zen, is used in IO32, 64, Titanium, PowerPC, right? So uh, and actually this Zen modifies Linux is at the lowest level and the most privileged layer or a hypervisor. One or more guest OS can run on top of the hypervisor. I repeat, one or more guest OS can run on top of the hypervisor. Clear? Now coming to the KVM. KVM stands for kernel based virtual machine, isn't it? So it is a Linux kernel virtualization infrastructure which supports hardware assisted virtualization and para-virtualization by using different frameworks. Intel VTX, AMD, Vito.io respectively. Right? And coming to this Vito.io framework, it includes a para-virtual Ethernet card and many more like disk controller, devices, adjusting memory, and interfaces, drivers, etc. Here, next, coming to in detail hardware support. Firstly, switching to CPU virtualization, as virtual machine is a duplicate of an existing computer system. It's a replica, right? In which a majority of virtual machine instructions are executed on the host processor, right? And there are some unprivileged instructions of virtual machines which can directly run on the host machine for higher efficiency. And what about the other? The other critical instructions should be handled carefully for correctness and stability. Clear. Now, here we have some critical instructions which are categorized into three. What are they? Privileged instruction, control sensitive instruction, and behavior sensitive instruction. Okay. Now, what is this critical is that privilege? First, we'll talk about privileged instruction. This execute in a privileged mode and will be trapped if executed out of this mode. Okay, so I just told you two types of modes: privileged mode, unprivileged mode. Okay, so during this mode, if any traps occurs, then definitely it will be identified. Now coming to the secondly, control sensitive instructions. This attempt is to change the configuration of the resources which were used. Clear. Now thirdly, behavior sensitive instructions. This have different behaviors. By the word itself you should understand. This might be having different behaviors which is depending upon configuration of resources, load, and what operation should be stored in the virtual memory. Clear? Now, in continuation with that, this architecture is virtualizable only if it supports ability to run the VM in privileged mode or unprivileged mode. Clear. Now, when the privileged instructions, including control and behavior sensitive instructions of VM which are executed, then they would be trapped in the VMM only. So, in this case, the VMM acts as unified mediator for hardware access from different virtual machines. Why? In order to guarantee the correctness and the stability of the whole system. Clear? Please do remember these two parameters, stability and correctness. Next, as it is said, not all CPU architectures are virtualizable, right? There's some architecture which can be naturally virtualized because of all control and behavior sensitive instructions are privileged instructions. What is RISC? What is the full form of RISC? Reduced instruction, and then oh, S is what? Single or a simple? Please find out and let me know. Right now, in the contrary, x86 CPU architectures are not primarily designed to support virtualization. This is because 10 sensitive instructions such as SGDG, which stands for Store Global Descriptor Table Register, and SMSW stands for Store Machine Status Word, are not privileged instructions. Means when these instructions execute in virtualization, they cannot be trapped. That is why these are not primarily designed. Now, upon Unix like system, a system called triggers some kind of interrupts and it passes the control to the OS kernel. Why? So that the interrupt handler in the kernel can be invoked to process the system call. Okay, see, whenever you do any activities with your computer system, what do? You will be interrupted with the kernel, right? Are you expecting this to do? Are you want this to be happen? Are you looking for this resources or not? But your action is being created an exception that because it is already existed in your computer system, you cannot completely execute this file because there are no supporting files. You cannot view the content of this file because you don't have installed supporting file, right? On a para virtualization system such as Zen, a system call in the guest OS first triggers. Okay, it will first trigger with this type of interrupts. Okay, almost at the same time, this interrupt, 82H interrupt, is also triggered. Incidentally, the control is passed on to the hypervisor as well. Okay, now when the hypervisor completes its task, when the hypervisor is nothing but what? VMM, right? When the hypervisor completes its task for the guest OS, system call it. Okay, now another thing, it passes the control back to the guest OS kernel. Okay, whenever it wants, it simply invokes it. Now, coming to the how does a hardware assist CPU virtualization? Yes, this technique is simply virtualized because of full or para virtualization, as it is complicated. And when we talk about the examples, Intel, AMD, it added an additional mode which is privileged mode, right? They are in which level? Ring 1. I just shown you the figure. Whenever it is in terms of VMM, then it is directly or indirectly call a particular rings, ring 0, ring 1, ring 2, like that. Okay, so some operating systems can still run on ring 0, and whereas hypervisor run on ring 1. Clear. And this technique removes the difficulty of implementing binary representation or binary translation of full virtualization. Okay, so I hope you remember what was the problem with full virtualization? Translating binary, right? Binary translation, implementation of binary translation was making a very big problem. So this can be removed. Clear. Now coming to the memory virtualization. Till now we have discussed about the CPU and in terms of hardware point of view, right? Now switching to memory virtualization, right? So what this virtualization is similar to a VM support, which is provided by I mean these days modern operating systems. Okay, whereas in traditional, the execution environment would be like this. The OS maintains mapping of virtual memory to machine memory by using different types of page tables, which is a one-stage mapping from virtual memory to machine memory, ensuring that whether uh, is it the exact one which is being requested or not. Okay, and all modern CPUs includes different types of functionalities like memory management, translation, look aside buffer. All these are data structures, right? So which keep track of uh, 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 like data related to a process. Okay, it means like for this process how much amount of memory is to be allocated, right? So there may be exchange of information from one functionality to another functionality. For that, what files does it require? What registers does it require for holding the data temporarily? Okay. Next, in virtual execution environment, this VMV, virtual memory virtualization, involves sharing the uh, physical system memory in RAM. So, what is the use of this? It is the advantage of dynamically allocating it to physical memory, right? Now, this can be viewed in two-stage mapping process, right? Which would be maintained by guest OS. Clear. So, firstly, virtual memory to physical memory. This is the first stage mapping, right? Then, second stage mapping is physical memory to machine memory. It means, can I say there is a transitive dependency from one to another. Virtual machine to physical memory. After the mapping is done, then the mapping of physical memory to machine memory is gonna done. So there is no direct contact from virtual memory to machine memory. Clear? And this uh, memory MMU should be supported, which is transparent to the guest OS. And then this guest OS continues to control the mapping of virtual address to physical memory. Then so on to machine memory. Now let's look at the figure. See here, as I said before, first these two things mapping should be done. Then whatever the output is gained in this block, then the mapping should be done among these two memories, right? Which is purely transparent to the guest OS, right? So there are two virtual machines, VM1 and VM2, and every virtual machine is busy with some processes, right? So for the execution of this process, there is a page table is to be maintained. That is this. Page table is exclusively for VM1 and another one is for VM2. So what is the use of page table means? See, currently both the processes are in busy, isn't it? So for process का मतलब ये है कि एक प्रोग्राम से प्रोसेस नहीं बनता. एक प्रोसेस के लिए कुछ फाइल चाहिए होते हैं, कुछ सिस्टम कॉल चाहिए होते हैं, कुछ मेमोरी चाहिए होते हैं, राइट? सो बाय कंबाइनिंग ऑल दोस थिंग्स इट बिकम्स अ process. It means I can say it is collection of jobs. Clearly. Now, for the execution of individual process, what does it do is, it needs some file. Okay. So मेरे को एक फाइल होना चाहिए था कि which helps me to compile my program. Right? Compiler I need. Right? Now, whichever the programs or the things are frequently used, all of them get stored in a page table. Now, similar fashion occurs to VM as well. Right? Now, what happens? First, these two processes will be checking is it available in this page table or not. If the page is fit, I mean, if the file is identified, file, then it is called as page hit. अगर नहीं मिला उसको बोलते page miss. Right? Now, with that it doesn't fail. What happens? Even after checking in this page table, it couldn't find. Then again it get back to the main table. Okay, so that is what is known as translation look aside buffer. Clear? I'm sorry, this is known as TLB and this is known as page table. Okay, पहले TLB में check करेंगे. Then उसके बाद if the page is not found, then it comes back to the page table. Okay, this page table is common for all the processes. This table is common for all the processes. Clear now? This is what the two-level memory mapping procedure. Now, just now we discussed about memory virtualization, right? Now we are moving on to I/O virtualization, which involves managing the routing of I/O requests between the virtual devices and physical devices. The physical devices obviously shared devices among the processors. Right now, at the time of writing, there are three ways to implement I/O virtualization: full device emulation, para virtualization, direct I/O. Right now, let's see look one after the other. Full device emulation is the first approach for I/O virtualization. So generally, this approach emulates well-known and real-world devices. Clear. It means all the functions of a device or bus infrastructure, such as device enumeration, identification, interrupts, everything is replicated in terms of software. Now let's move on to the figure. See here. This figure depicts what? Device emulation for I/O virtualization implementation inside the middle layer that maps I/O devices into the virtual devices for the guest device driver to use. This is what the guest device driver, right? All these are middle layer, right? Now, the single hardware device can be shared by multiple virtual machines. I repeat, a single hardware device can be shared by multiple virtual machines that run concurrently. But again, the concurrency leads to deadlock. Okay, so because of this, I can say the software emulation runs much slower than the hardware. Clear. So here you have some detailed information like this is known as virtual device, which is allocated to guest device driver, and what happens in the virtualization layer, emulating the virtual device, and then mapping whether it is correct or not by identifying real I/O addresses and assigning physical devices by looking at the features, etc. etc. In addition to the I/O virtualization, the para-virtualization method of I/O virtualization is typically using Xen hypervisor. It is also known as split driver model, having front-end driver, back-end driver. Okay, so what is front-end driver is running in domain U, some U. Uh, I think U is a user here. Okay, and the backend driver is running in domain O. So I can say O is owner here, and they interact with each other via shared memory. Clear. Now, what does a front end driver do is it manages the IO request. What all the requests are coming to IO, it manages it, and uh, the backend the driver is responsible for managing the real IO devices. Okay. Next, direct IO virtualization, which lets the VM access the devices directly. So, as name depicts, direct accessing directly the devices. So, it can achieve close to native performance without high CPU cost. Right now, however, it has a direct IO virtualization which implements focusing on networking mainframes. And not only that, there are a lot of challenges which is being made on hardware devices. For example, when a physical device is reclaimed, it means for migration, it may have been set to some state like DMA to, I mean, direct memory access to some memory locations, and that can be function incorrectly, or even what happens sometimes the whole system may crash, right? And since this software-based I/O virtualization requires very high overhead of device emulation, hardware assisted I/O virtualization, so it leads to critical state. Next, virtual clusters and resource management. So about a cluster we've already discussed, and if it is virtually clustered and how the resources are managed among the virtual machines, this we will find out now. So as it says, a physical cluster is a collection of servers. It means a physical machines which are interconnected by some type of network, as the author given an example over here as LAN. But basically now see, we are connected from your end and from my end, sitting somewhere, some locations, with which type of network? It is in city, right? But we are not using connection oriented, everything is wireless oriented. So it can depict metropolitan man network. Okay, fine. Now in this section we will study three critical design issues of what virtual clusters. They are line migration, memory and file migration, deployment, dynamic deployment of virtual clusters, right? So what I want to just tell you is, when a traditional VM is installed, the administrator needs to manually write configuration information. Okay, if it is traditional, manually should be written, or it should be specified that what are the sources of configuration. It means it helps it helps the VMs to join which type of network. Is there any insufficient of configuration, any problems to cause with overloading and all, right? So here we have an example of Amazon Elastic Compute Cloud, EC2, Amazon's Elastic Compute Cloud. So it's a very good example of web service that provides elastic computing. So what is this EC2 permits us? It permits the customers to create VM and to manage user accounts over the time of their use. See, let's say, I don't know how many of you are habituated being used online shopping, right? Now, there are many more of online shopping sites. Let's say, what do? I, I simply um, choose the products, right? I choose them, or some of them simply to check out the prices. Sorry, the prices of the products, right? They don't do online shopping. Their service is to just see the product details, right? And uh, that is one service. Now, how does it elastic is? See, I am doing payment. Now I want to buy it. If I want to buy it, I have to give my credentials, isn't it? Now, the what extra services can be added to the user is, I can, I mean, upon my multiple transactions, multiple purchases over the same shopping site, I may be credited with some points, isn't it? So that's how elastic is. Depending upon the demand of users, the services have been added. It is purely pay on usage. Clear. How extent you want to make use of those services, that elasticity this will provide. Okay, so one of the web services, Amazon. Clear. Now coming to the differentiation among the physical and virtual clusters. Both of them are with VM installed, and both of them are having distributed servers, right? And which are interconnected logically with some type networks. Let us see in detail about how does it actually represented in terms of diagrammatical representation. See here, this is a figure. A cloud platform with 4 virtual clusters. 1, 2, 3, and 4. Right? The virtual cluster boundaries are shown as distinct boundaries. So you can see here the dashed lines of virtual 1, and these are the virtual 2, and these are virtual 4 and 3, right? So the provisioning of virtual machines to a virtual is done purely dynamically, only if they satisfy some properties. What are they? See, how many virtual cluster nodes are there? 4, right? So these virtual cluster nodes can be either physical or virtual, isn't it? Physical or virtual. Now, multiple VMs running with different OSs can be deployed on the same physical node. See here, if you look at the physical cluster 1, some of them are belongs to virtual cluster 1 and some of them are belongs to virtual cluster 3, isn't it? Now, a VM run with a guest OS, which is purely different from the host OS. Then how does it manage? Yes, it manage. That is what the beauty of this cloud computing. That manages the resources in physical machine with which the virtual machine is implemented. Clear. And the purpose of VM is to consolidate with multiple functionalities on the same server. Right. Now, what is the objective of this is to enhance server utilization, application flexibility, etc. etc. Right. So all these VMs are kept and replicated together in multiple servers in order to promote distributed parallelism, fault tolerance, and disaster recovery. Right. So that the size of virtual clusters, the size of virtual clusters can grow or shrink dynamically. How? It means if I don't need the first physical cluster resources, so what do I do? If I don't need, I simply uh, do not use of them. Okay, I simply deny accessing them. Right? Then what happens? My virtual first cluster is restricted to only this. So what happens in that perspective? The size will reduces. Clear. And yes, there is a possibility of failures. Failure of any physical node may disable some virtual machines installed on the failing node. Okay, let me tell you here. If a physical node is failed, so this physical node is requirements is being under the usage of virtual cluster 1 and virtual cluster 3. Only these two will be taken away, but it will not disturb the entire host system. Clear? Now let me move on, as this I've already covered in the previous slide itself. Okay, so now here see very much in detail about physical and virtual clusters in different aspects. I'll show you and help you out to understand in the mathematical representation. See, this figure shows the concept of a virtual cluster based on the application, partitioning, and or customization. Okay, now you can see here there are four different colors, right, in the figure which represents the nodes in the different clusters. Right? So, as the large number of VM images present, the most important thing is to determine how to store these images in the system efficiently. How to store them in an efficient manner. Okay, so there are simply common installations where most of the users or applications like operating system, user level programming libraries, and these software packages can be pre-installed as a template, which is called as VM. Right? So with these templates, user can build their own software stack. Right? Now, new OS instance can be copied from the template. Right? Not only that, the programming libraries, applications do also instantly install. Clear. Now, the representation of physical clusters we have just seen in the previous slide itself. Right? As the physical machines are also hosted, called host systems, and in contrast to that, VMs are guest system, and if they run with different operating system, each VM can be installed on a remote server and it replicated on multiple servers belonging to the same or different physical clusters, and depending upon the usage, some of the VM nodes can be removed or added, which can be done dynamically, right? So this is how it happens. Clear. So how many VMMs are there? 5 VMMs are there. 5 VMMs are using different VMs of different applications, right? Which are clustered together. One cluster, two cluster, three and four clusters. Right now, let us see in detail about the verses of these two types of clusters, which are depicted in terms of physical and virtual clusters. Yes, the fast deployment and effective scheduling also does a fast deployment. Let's see how. The systems should have the capability of fast deployment, which depicts in two ways: to construct and distribute software stacks like OS, libraries, and some applications to a physical node inside clusters as fast as possible. All these things have to be constructed and distributed among themselves. Now, to quickly switch routine runtime environment from one virtual cluster to another virtual cluster, if one user finishes using system, the corresponding virtual cluster should shut down or suspend quickly. Why? To save the resources to run on another virtual machine which is not used. Why does it should be in running mode? If it is suspended, then the same server can be used to another virtual cluster, isn't it? So this quite dynamically work out in these clusters, right? And yeah, the concept of green computing has most attracted, uh, uh, which was, I mean, very recently. And the previous approaches have also focused on how to save the energy in terms of cost point of view and maintaining in a single workstation, and which consequently do not necessarily reduce the power consumption of the whole cluster. Right. If anything, one failures, it should get from the another one. It should not disturb or destroy the entire system. Right. This kind of live migration of VMs allows workload of one node to transfer another node. अगर एक पे बहुत workload हो जा रहा है, right? On one virtual machine, the workload is very much, right? And there is another virtual machine which is simply idle, right? So in order to balance and remove the overhead of this virtual machine, what it can do is it can give some amount of workload to another virtual machine by knowing is the status, what the status of this virtual machine. Is it idle? Is it overhead? Or is it having or dealing with some task? If no, then some of the work can be transferred to another virtual machine in order to balance the load, right? Another one is another advantage of virtualization is it also does a load balancing. That just what I mentioned, right? And uh, it also has a very good characteristic that scale up and scale down, scale up and scale down. See, as I just said now, depending upon my usage, I request, and upon my request, the services are granted to me. So my activities will automatically scale up, right? Now if I don't need, because बहुत सारा I mean credits मेरे को नहीं आ रहे, but I'm losing my amount, right? Now what do? I simply reject accessing that. Scales down. It not only improves, I mean you will be benefited in cost perspective, but also it also improves your performance, right? Yes. Upon that, high performance virtual storage can also be maintained when when it includes pre-installed operating system without certain application softwares. And this template VM can be distributed to several physical hosts in order to customize the virtual machines. Okay. In addition to that, existing software packages reduce the time for customization. And it is very important to efficiently manage the disk space, which is occupied by template software packages, right? Which helps to reduce duplicate blocks, right? And basically there are four steps to deploy a group of virtual machine or target cluster, like preparing the disk image, configuring the virtual machines, choosing the destination nodes, executing, the virtual machine deployment command on every host, right? So these templates could implement the some one type of format. What is that? Cow. It means stands for copy on write, right? Now what does this cow do is, a new cow backup file is very small and it is easy to create and transfer. Therefore, it reduces disk space consumption. Okay, and it is very much shorter, copying the whole raw image file.